Chapter 4.3 Current carrying conductor in a magnetic field. A setup like this, with a battery and two magnets, together with a wire, may be the simplest design of an electric car. In this chapter, you will see how a magnetic field may exert a force on a current carrying conductor, such as a wire. In the following experiment, there is a magnetic field produced by two slab-shaped magnets with their opposite poles facing each other, so that there is a downward magnetic field. There are also two rails, and then there's a rider where the rider has a current to flow. In this case, the current is flowing out of the paper. You will see in the video that the rider, which is a metal rod, is pushed to the right, which shows that the magnetic field produces a force on the current carrying rider and push it to the right hand side. Now let's take a look of the video.
We will find out how the magnetic force on a current carrying conductor is affected by the current and the length of current inside the magnetic field. Set up a current balance. Adjust the position of the wire until it is balanced. Set the reading of the electronic balance to 0. Switch on the power supply. Vary the current flowing through the wire by changing the resistance of the rheostat. Take the readings of the ammeter and the electronic balance. The reading of the electronic balance gives the magnetic force acting on the current carrying arm. Repeat several times with other current values. Record the results. Plot a graph of the magnetic force F on the wire against the current I through the wire. How is F related to I? Now pass a fixed current of 3 amperes through the wire. Measure the length of the slab-shaped magnets. This represents the length of the current inside the magnetic field. Then, take the reading of the electronic balance. Record the results. Add 1 and 2 pairs of slab-shaped magnets round the current-carrying arm in turn to double and triple the length of the current inside the magnetic field. Record the reading of the electronic balance in each case. Plot a graph of the magnetic force F on wire against the length L of the current inside the magnetic field. How is F related to L?
So in the last part of the video, you may notice that when the current is flowing out of the paper and the magnetic field directs downward, then there will be a magnetic force that acts on the current carrying conductor to push it to the right hand side. By the way, the force depends on the current. It also depends on the magnetic field. To help people to remember the direction of the induced force, we use the famous left-hand rule. Such as in this case, when the magnetic field directs to the right and the current flowing out of the paper, then there should be a force that points upward. So I will try to show you this in the next lesson. So using our left hand, then we represent the case like this, with our pointer pointing in the direction of the magnetic field, and the middle finger pointing in the direction of the current. Then the thumb will point in the direction of the induced force, the force that is produced in this case. Feynman's left-hand rule does not explain why there is a force. It only helps you to remember the direction of the induced force. To represent the situation, we may use a 3D diagram like this, so that the magnetic field points to the right hand side, just like in this diagram, the current flowing out of the paper just like this in the diagram, and then the force will point upward. On the other hand, you may also use a 2D representation, which is usually easier to draw. So in this case, the magnetic field pointing to the right and current flowing out of the paper, we use a single dot to represent this, so that the induced force on the current carrying conductor points upward. Now let's see what may result when an electron enters a magnetic field. First, the electron is negatively charged. When it is moving to the right, that means the current is moving to the left. It is important to know the direction of the current. So you see that the current points to the left, while magnetic field points into the paper will produce a magnetic force, which according to left-hand rule points downward. So the motion of the electron is deflected and it will go this way, so that its velocity changes in direction. In this way, the direction of the current will point to the top left, and using the left-hand rule, you may find a new magnetic force pointing to that direction, which further moves the electron along a circular path like this. And so its new direction of velocity and the respective current flow will produce a new force, which continuously changes the direction of the electron, and you can see the electron goes along a circular path. So sooner or later, the electron will travel along a semicircle and then finally flow out of the magnetic field. And later on you will see how the radius of the semicircle depends on the size of the magnetic field and the current flow. And now would you try check point 5? And after that we will look at the factors affecting the size of the magnetic force. So in the next two experiments, you will see the factors that affect the size of the magnetic field. So that eventually you will find that the magnetic field depends on the size of the current, the length of the wire inside the magnetic field, and the strength of the magnetic field itself. And now let's take a look at the first experiment. They make use of a special apparatus called current balance. A current balance is a rectangular coil of wire, and with current flow, we may measure the size of the magnetic force acting on it. We have to adjust the position of the rectangular coil until it is balanced. We use an electronic balance to measure the magnetic force acting on it. This is the electronic balance. We use it to measure the magnetic force acting on the current balance. On one side of the current balance, there is slab-shaped magnet, so that there is current flow along the circuit, and this current flows through a magnetic field produced by the slab-shaped magnets. It will experience a force, such as in this case, an upward force, so that the other side of the balance will push on the electronic balance, and you will find the electronic balance reading increases. With different currents flow, there will be different readings on the electronic balance, which are the magnetic force produced by different currents. And I have some readings here. With different currents, then there are different magnetic force produced as measured by the electronic balance. I then plot a graph of magnetic force versus current flow through the wire, and they are found to be directly proportional. For the second part of the experiment, we fix the current, but then we change the length of the wire inside the magnetic field. We arrange more numbers of slab-shaped magnets in this way, so that there can be different lengths of wire inside the magnetic field. And of course, you will find that the force applied on the current balance increases when the length of wire inside the magnetic field increases. And this shows the experimental results. When the length L increases, then the force produced also increases. Then we plot a graph of magnetic force versus length of current inside the magnetic field, and they are found to be directly proportional. Be careful that in this case we fix the current so that we may compare the length of wire inside the magnetic field with the force produced. Now let's take a look of the video of the experiment.
Set up the Fleming's apparatus. Switch on the power supply and watch for another motion of the rider. Repeat by turning the magnets around. Repeat by reversing the current.
So we know that a larger magnetic force is produced when there is a longer length of wire inside the magnetic field, or there is a larger current. But how does the strength of magnetic field affect the size of the magnetic force? To find the relationship, we use a flat solenoid to produce a magnetic field, which depends on the current flowing in the solenoid, so that we may change the current flow in the solenoid to adjust the magnetic field inside the flat solenoid. You may refer to page 165 to see how the current flow inside the solenoid may then change the magnetic field produced. In this case, we change the current flow in the solenoid without change the current flowing in the current balance. You will see when the current flow in the solenoid changes, because the magnetic field inside changes, so the magnetic force produced also changes. Simply speaking, we adjust the flat solenoid current so that there is a change in the current balance reading, which is the change in the magnetic force. And as what you may expect, the magnetic force produced depends on the strength of the magnetic field inside the flat solenoid, and they are directly proportional. Simply speaking, a larger magnetic field produces a larger magnetic force on the current carrying wire. In fact, other than changing the current inside the flat solenoid, we may also use slab-shaped magnets, and by arranging them in this way, we may change the magnetic field in this experiment so that we may measure the magnetic force produced. And now let's take a look of the experiment.
We will find out how the magnetic force on a current-carrying conductor is affected by the magnetic field strength. Set up a current balance. Adjust the position of the wire until it is balanced. Set the reading of the electronic balance to 0. Connect a flat solenoid in series with a rheostat, an ammeter, and a DC power supply. Place the current-carrying arm of the current balance inside the flat solenoid. Pass a fixed current of 3 amperes through the wire of the current balance. Switch on the power supply connecting to the flat solenoid. Vary the current flowing through the solenoid by changing the resistance of the rheostat. The magnetic field strength is directly proportional to the current flowing through the solenoid. Take the reading of the ammeter connecting to the flat solenoid and the reading of the electronic balance. Record the results. Repeat several times with other current values through the flat solenoid to obtain different sets of data. Then plot a graph of the magnetic force F on the wire against the magnetic field strength B. How is the magnetic force F on the wire related to the magnetic field strength B?
So you see how we may find the relationship between the force and the current flow in the current carrying wire, as well as between the force and the length of the wire inside magnetic field, and also the relationship between the force and the magnetic field. Of course, they are all directly proportional, and in this case, the magnetic force is directly proportional to the product of BIL. And we may write the equation F equals K multiplied with BIL. K is taken to be 1, and the unit in this case is called Tesla. So 1 Tesla is such a magnetic field. When there is a 1 meter length of wire inside the magnetic field with a current flow of 1A, it experiences a force of 1 Newton. Now let's take a look at the following example to see how we may apply the formula F equals BIL. Now first, you can see there is a length of 5 cm of wire inside a magnetic field. That makes the balance reading changes from 145 gram to 146.5 gram. That is to say, there is a downward force acting on the current balance to make the reading larger when there is current flow in the wire. According to Newton's third law, there must be an upward force acting on the wire because these two forces are action-reaction pair. According to what the question say, the current flows from X to Y. So current flow from X to Y in this direction, and then there is a upward force produced. Then you may apply your left hand rule and you may find the magnetic field pointing in this direction. That is to say, on the side of P there is a north pole, on the side of Q there is a south pole. And so in this way, you should be able to answer question A and B. And for C, to find the magnitude of magnetic field, we use the formula B equals F over IL, where F is the force acting on the balance due to current flow, and that is the difference between the two readings in gram. You have to divide this by 1000 and multiply it with 10 meter per second square. In this way, you may change it back to force in Newton, divided by the current 2A and the length 0.05 meter. Then you may find the magnetic field strength 0.15 Tesla. So for the rest of the question, would you read it yourself to see if you follow? Now I will skip a page here, and would you please take a look of example 10. In this example, you can see two wires carrying like currents. These two currents are both flowing out of paper, and you will find that these two wires are going to attract each other. So let me start. What you do first of all is to find the magnetic field by current X on the left hand side. This is X. There is a current flowing out of the paper. You may now use the right hand rule, the same as on that page, so that you may find X is producing a anti-clockwise magnetic field like this. And so at position Y, the magnetic field points upward. And now you may find that the current at Y flowing out of paper and experiences a magnetic field by X pointing upward. And now you have to use the famous left-hand rule to find the induced force. And in this way, you may find that the wire at Y experience a force to the left-hand side. And check carefully if you cannot. After that, we do the same for the wire at X. Now we find, first of all, the magnetic field produced by Y. At X, you may use your right-hand rule. In this way, with the thumb pointing out of the paper at y, and then your finger will follow in the anti-clockwise direction again. So that magnetic field produced by y at the position of x will be downward. And so you may now start to use your left hand rule here. With your left hand rule, that is the pointer pointing to yourself and the middle finger pointing out of the paper, you should find your thumb pointing to the right hand side. And in this way, the two forces attract the two wires together. But this is only the beginning. This is for part A. You are now going to find the magnetic field produced by each wire, as well as to find the force per unit length. To find the magnetic field produced by a long wire, you use the formula B equals mu log I over 2 pi r, which may be found on the formula sheet. And this magnetic field is rather small, and in that case, substitute into the formula, you may find the induced force when such a magnetic field adds on a current flow of 2A with a length 1 meter, so that you may find the force per unit length, that is, the force per 1 meter of wire. So from the above example, you may know that we may use that formula to find the magnetic field produced by a single wire first, and then using the formula BIL, you may find the force acting on the second wire with a current I2. In this case, the force between two wires is given by this formula F equals mu log I1 I2 L over 2 pi r, where L is their common length. And so you may find the force per unit length F over L, which is mu log I1 I2 over 2 pi r. As from example 10, you may see when the two currents are flowing in the same direction, then these two like currents attract each other. While you may also try this when the currents are flowing in opposite directions, then the forces on them direct in opposite directions as well, so that these unlike currents, they repel each other. And this gives a new definition of the unit ampere. In this way, 1 ampere of current is the current flowing in two infinitely long, thin, straight, parallel wires when they are separated by 1 meter in vacuum, and produce a force per unit length of 2 times 10 to the power negative 7 Newton, which is actually making use of the above formula, in which case we have force per unit length 2 times 10 to the power negative 7 Newton, and that should be equals to mu log, which is 4 pi times 10 to the power negative 7, multiplied with the product of the two currents, and both of them are 1, and then divided by 2 pi, and the separation 1 meter. And it is now time for you to do the checkpoint 6. And for page 179, we will discuss it in the next lesson.